suppose L is regular. Suppose I give you a language L, and it's regular. We're going to consider the complement of L. So I'm going to denote this as L bar. So you might ask, Dan, what is the complement of a language? Well, imagine I give you, so I imagine I have my strings in my language, right? What the complement is that you take all possible strings, you take away the ones that belong to the language in question. It's everything that isn't in the original language, but doesn't include what's in the original language. Is that clear? So just think about it like this. So imagine I give you, so here's my language. Everything outside of the language is outside this circle, right? So what I need to do is the complement would simply be all of the strings that don't belong to that language. So that's what the complement of a language is. So what I want to do for you is I'm going to show you how if you take the complement of a regular language, you still end up with a regular language. So we're going to prove this here together. So naturally, the strategy here is going to be that, okay, so imagine I have a language L. What by definition, that means that there exists a DFA that recognizes that language. I'm going to show you how to build another DFA using this DFA and show that there's actually a property that this new DFA has in relation to the original one. It's going to be surprisingly simple. It might be the first thing you might think about trying to do. And we'll see an example of how you use this. So that's the game plan. So by definition, there exists a DFA M. So I'm going to give it a name. I'll call it M. Q sigma delta Q0 F. You might recognize this 5 tuple from the definition. That recognizes L, which is going to, of course, be equal to the language of M. Right? So now I'm going to show you how you take and create another DFA. So consider M bar. I'm just going to call it M bar. That's its name. I could have called it Bob for all I care. It's just a name. It's going to be Q sigma. So it's going to have the same 5 tuple with one change. And you might ask, okay, so Dan, what's going to be different here? It's going to be that we're going to make the set of final states be something that will feel a little bit natural to what I just described up here. So you recall that the set of final states, when a DFA reads an input string, it makes transitions by reading symbol by symbol, right? And it accepts if the DFA is in one of the states that's a final state, right? Well, what I am proposing to you is that you should be able to just simply consider this new set of final states to be every state but the original final states. So we'll see an example after the proof. So that's what this says. This is Q set minus F. So I'm just taking the set of states. I'm removing the final states from it. So it's just going to be everything that isn't one of the final states. So it's every non-final state becomes a final state. And all the final states of the original DFA are now non-final. So now, observe. So think about now how the execution of a DFA works. So it reads symbol by symbol, the input string, and it'll end up in a state, right? At the end of this. Well, let's think about what that means within the definition of acceptance of a DFA. So observe that when M finishes, so that's the original DFA, finishes reading W, reading string W. If W is in the language L, that's what it means, is in, it accepts as it is in a final state. I'll say it like this, in a state of F, which is the set of final states. And what happens when W isn't in the language? What happens? What happens? So if it's in the language, it accepts it, right? Because it'll land up in a final state of M. Well, think about it. And whenever W isn't in the language, it rejects, right? Why? Because it won't be in one of the final states. As M is in a non-final state. So take a look now at how we constructed M bar. So notice that it accepts, in this case, because it was in one of these states here, and rejects when it's in a non-final state. Do you notice that now all I've done is I've just taken all the states that were non-final states, but now they're final states in the new DFA. So do you notice very quickly that this is going to be where it's going to flip the reasoning here, right? So notice that it's going to be now that if W is in the language, it's going to reject, right? Because now those states are now non-final, and it's going to accept whenever it's not in the language, right? But what does that mean? What does that mean? Well, think about it. If these are all the possible strings inside of this circle, or whatever this is going to be all the strings in the language, right? The DFA originally accepted all the ones in this circle. It rejects all the ones I've just shaded outside of it. So, however, now what I've done is I've just simply flipped the sucker. So now what's going to happen is it's going to now accept all the ones out here and reject all the ones inside the funny circle. So by construction, whenever W is accepted by M, W will be rejected by M bar. Similarly, any string W that isn't in the language, L, will be rejected by M. For what reason? What's the reason why it rejects again? Because it's in a non-final state, right? As M will be in a non-final state. In a non-final state. So this state will be a final state in M bar, right? So Similarly, any string W not in the language L will be rejected by M, as M will be in a non-final state, right? So this state, so the one it would be going to, will be a final state in M bar. In M bar. But what does that mean for M bar, for that string W? What does it do? What's it going to do? It's going to accept, right? As every string not in L is in L bar, right? The complement of the language consists of all the strings not in L, right? It follows that M bar, so here's the big connection. M bar accepts a string W, if and only if W is in L bar. Therefore, since I've just presented to you now a DFA that has this property, it will accept L bar. So in fact, it decides it. It recognizes the language. It means that L bar is regular. And that completes the proof. So let's see an example of how simple this little tweak can be. So let's consider an example similar to one I think I may have mentioned in the past. So I'm going to draw its transition diagram. So I'm going to give you a DFA. It's going to have two states, Q0 and Q1. Q0 and Q1, they'll stay in their respective states whenever it reads a 1. It'll flip to the other state upon reading a 0. So this is what M would be. For example, if I gave you a given DFA. So notice that Q0 is the final state. So what should happen then if I wanted to make this DFA recognize whatever this DFA would reject, meaning that it's the complement, right? So what would I do to this DFA? What change do I need to make based on what we just discussed here? So while you're thinking about that, I'll remind you what this DFA will recognize. So notice that this DFA so notice it stays in Q0. If, say, for example, you read no zeros, it stays in Q0, right? Because it'll just read ones, right? Or it'll just be finished reading the input. Whenever it reads a 0, it goes to Q1, then reads another 0, it goes back to Q0. Do you notice that there has to be a property of how many times 0 appears in the string, right? For example, if I give you a string that looks like this, like 0, 0, 0, 1, notice that it'll go Q0 to Q1, Q1 to back to Q0, and then it will go Q0, Q1, and then it reads the 1, stays in Q1. It would reject this string. So what property does this, like what kind of strings does this DFA accept then? It accepts strings with an even number of zeros. So any binary string with an even number of zeros, this DFA will accept it. That's what it recognizes. It recognizes all binary strings with an even number of zeros, right? So let's see what happens. So you know that if I wanted to get every other string, you know it's going to actually have to be these ones, for example, ones with an odd number of zeros. So if you have that intuition in mind, you'll notice that this is going to feel very natural for this example, but you'll notice I'm not going to be specifically tailoring it to this example. It's just to help you see how I could tweak with it. So if I wanted to get my M prime in the proof, all I do is I take all of the what used to be final states, I'm going to make them non-final, and I'm going to assign all the other states of the original DFA to be final states. So in this case, all I'm going to do is I'm going to swap which ones of these are the final states. So in this case, Q0 is now non-final. Q1 is going to be a final state. I'm not going to touch anything else. And that's how we're going to construct a DFA that accepts the complement of language L, where L would be the language that's recognized by M. So you notice very quickly with this example that we have on the board over here, that whenever I have an odd number of zeros now, it accepts. Whenever now it has an even number, it rejects. So you could do this with any DFA. So this is a really simple little tweak you can make if ever you want to get the strings that are not a part of your language. So all the ones that are not part of the language. So please just keep in mind though, and this is very important to remember, is that the language in question here is a regular language. If it isn't regular, it may not be the case that it's actually going to result in the same kind of language. In this case, a regular language. In this certain circumstance, because it's a regular language, we've shown that the complement of that language remains regular. Pretty neat, right?